All right, give me 1 second. All right, works.
Excellent. Okay, I think we can get started. Good morning, good afternoon, everybody, wherever you happen to be in the world right now. So welcome to Rocky World's discussions. The schedule here, as usual, is going to be that I will give a brief introduction and then pass over to our speaker, who's going to talk for approximately 30 to 40 minutes. We'll then follow that up with a plenum discussion for the remainder of the hour, and then close after that point. And just a quick reminder that the usual netiquette rules, Zoom usage rules applies here. Please use your full name when you're logging in or when you're asking questions. Keep muted when you're not asking questions. And if possible, turn your video on when speaking, so we can see who you are. But that is optional. Okay, so today's speaker is, we're happy to welcome Lars Buchhave. Lars is a professor at the National Space Institute of the Technical University of Denmark, and he works on the discovery and characterization of exoplanets, including their composition and internal structure and atmospheric properties. Some of his notable work in the past has revealed the links between planet occurrence and host star metallicity, but he does a whole bunch of other things beside that as well. And so today he's going to be talking to us about the detection and characterization of terrestrial exoplanets with, it sounds like, a particular focus on Earth-like planets, including their atmospheres and habitability. So over to you, Lars.
Thank you so much. Should I try to share my screen?
I will stop share.
All right, let me see.
Go ahead when you're ready.
Work. You see this? This over here.
Looks good.
All right. So yeah, thank you so much for the invitation to talk today. As you said, I'm Lars Buchhave. I'm a professor at DTU Space. This is the National Space Institute at the Technical University of Denmark. And yeah, the title of my talk is Detecting and Characterizing Terrestrial Exoplanets. So, I mean, the last 30 years of exoplanet, or almost 30 years of exoplanet research has revealed like a ton of different exciting discoveries, of course. But if I were like pressed to come up with one single thing I think is exciting, it would probably be the fact that small planets have turned out to be incredibly common. And so there's of course, a number of different, many different papers on this. I've highlighted one here from a few years ago by Steve Bryson, or led by Steve Bryson. So basically, this is a Kepler mission legacy paper, I would call it, where Steve and team looked at the occurrence rate of habitable zone Earth-sized planets orbiting solar-type stars. By also doing injection and recovery tests in the Kepler data. And so this elusive Eta-Earth is being assessed here. And there's a few numbers here highlighted in yellow, and I'll try to unpack them just a little bit, not spend too long on this, but basically it depends on, the four numbers depend on how you extrapolate the data, if you're conservative or you're very optimistic. And there's also two different habitable zones, the conservative habitable zone or the optimistic habitable zone. So if you take the most conservative extrapolation and the conservative habitable zone, this paper comes, its conclusion is that about 0.4, there's about 0.4 Earth-sized planets in the habitable zone orbiting solar-type stars with some fairly large uncertainties, of course. If you go to the other extreme, the most optimistic extreme, the number comes to 0.9 with also sort of large uncertainties. But the point here is that this number is very large. I don't think the final word has been said on the exact occurrence rate of Eta-Earth or habitable zone Earth-like planets around solar-type stars. But the excitement here, to me, is that that means that there's really many of these planets in our astronomical backyard, meaning that we can analyze, detect, and characterize these planets because we have the required amount of photons Conversely, if this number was tiny, we would have to look, very far away to find these planets. But this is, to me, what excites me about the coming decades is that this number is fairly large, so that we can really dig into the planets in our astronomical backyard. So our group, I think, is focused. We're really excited about the small planets. This is very difficult work, but we're kind of focusing on two what we see as two major opportunities for terrestrial exoplanets. So one is the possibility of characterizing the atmospheres of Earth-sized planets, of course, orbiting cooler M-dwarf stars with James Webb and other instruments that are coming up, which I find is extremely exciting. This is the first time we potentially have access to do this, to really characterize secondary atmospheres around terrestrial planets. And the other area we're interested in is really trying to discover true Earth analogs. So basically Earth-sized planets orbiting solar-type stars in the habitable zone. And this is, of course, extremely difficult and elusive, but one of these things that will lead to these next-generation telescopes that want to look at the atmospheres of true Earth analogs and search for biosignatures in their atmospheres. So if we talk about the first area, characterizing the environments of terrestrial planets, the opportunity here is that we can now, for the first time, perhaps look at a secondary highly mean molecular weight atmosphere orbiting an M-dwarf, or a planet orbiting an M-dwarf. And of course, this is a very different environment than solar-type stars. These planetary systems are very compact, usually packed systems, and the proximity of the planets is much closer to the host star than in the solar system. And we also know that M-dwarfs have a very young active phase. They also have a lot of flaring and so on and so forth, and UV in the early stages. So it's likely that some of the close-in planets will have their atmospheres eroded over time. But it could also be that some of the planets further out perhaps retain their atmosphere and are maybe able to replenish them over time via outgassing or other volcanic activity or outgassing from the interior. So the zero thought question is basically, I would think, is do any of these planets retain atmospheres at all or replenish their atmospheres around M-dwarfs, and where is that kind of the transition from planets that have lost their atmospheres to planets that actually have atmospheres? And if there are some of those planets that do retain atmospheres, the next question, of course, is what is the composition and diversity of these atmospheres? I find that truly exciting. I mean, we know of the terrestrial planets in our solar system, and just among those, we have a very wide range of environments from Venus with this 100 bar CO2 dominated atmosphere and 500 degrees centigrade on the surface, to the Earth, and then to Mars with a very thin CO2 dominated atmosphere. And of course, the next question is, to what extent are atmospheres of terrestrial planets habitable, or are they at all? So for me, this is really very exciting, having been in this field some time now, that we're actually potentially able to study these secondary atmospheres for the first time. Of course, there's been work that's gone into this before James Webb was launched, with ground-based observatories and the Hubble Space Telescope in particular. And I'm showing here sort of a plot of the equilibrium temperature of small planets below 1.8 Earth radii that are close to us, and the transmission spectroscopy metrics on the vertical axis. So basically, planets up here are easier to observe. And the postdoc in our group, Hannah Diamond-Lowe, has been one of the people pioneering this work and trying to rule out the existence or rule in the existence of a hydrogen-helium dominated atmosphere around these small planets. And so you can see in this diagram, the ones with red crosses have been determined to not have sort of these hydrogen-helium dominated atmospheres. And maybe that's not super surprising that terrestrial planets are unable to hold on to a hydrogen-dominated atmosphere, but in any case, most of these planets that have been expected don't have these extended atmospheres. And just to sort of put it into perspective, I kind of like this slide, which is basically Venus eclipsing the sun up here on the left, and then a close-in actual picture of Venus. And as you know, Venus is about the size of the Earth, so we're about 6,400 kilometers in radius, and the atmosphere of Earth is 99% of the mass is within 100 kilometers. And so what you're seeing here is this very, very thin outline on Venus on the zoomed-in picture of the atmosphere of Venus. And what we're really trying to measure here is the size of that atmosphere as a function of wavelengths to get the transmission spectrum. And that is excruciatingly difficult, but it just sort of seeing this picture reminds me basically of the difficulty of this task. And then you, of course, have stellar activity and spots and so on and so forth interfering with your measurements. So this is really, truly very, very difficult. But we do have the opportunity of observing these terrestrial planets around M dwarfs. And of course, as you know, that means that we just get a much larger transit signal compared to if the planet was orbiting or transiting a solar type star. These types of planet stars are really not within reach. I think with James Webb, that would be excruciatingly difficult. So we have to go to these smaller red M dwarf stars in order to be able to perhaps detect atmospheres of terrestrial planets for the foreseeable future, I think. And of course, the instruments that are available to do this is the James Webb Space Telescope, which was launched a few years ago. And we have a program on TRAPPIST-1C. I'll come back to that in the coming slides. And then there's the ELT, which has first light in the end of this decade. And then there's a secondary instrument called ANDES, the high resolution spectrograph, which is right now being planned, and the hope is that it will have first light in the early 2030s. And ANDES will really be a workhorse for exoplanetary atmospheres. I think it's 100,000 resolution with a wide spectral range from 0.4 to 2.4 microns is the envision. And I put the slide on just to sort of put into perspective that the science case priorities that are driving the design of this instrument, there are four different areas, and two of those are exoplanetary atmospheres, one via transmission spectroscopy and a potential for detection of biosignatures, and then via reflection spectroscopy, which is going to be even very difficult as well. But the point is here that two of the four main science drivers for ANDES is basically exoplanet atmospheres. So that's going to be exciting. What ANDES will be able to do remains to be seen. It's still under design, and they're still talking about the actual how ANDES will come to be and the funding as well, which is difficult. As you know, ANDES is no longer funded as part of the ELT. It's a second generation instrument that Europe will basically, or the people behind ELT will have to get funding, national funding to fund. So that's also remains to be seen if that pans out. And so here's a turning to JWST. Here's a plot of the small planets and their equilibrium temperature of the ones that are scheduled for observations in cycle 1. So there's actually quite a few terrestrial-sized planets that will be observed with JWST. Now that doesn't mean that these will all result in detections of the atmospheres. There are various programs. Some are guest observer programs, and many of them are GTO programs, in fact. And so there will, in some cases, be a few transits available in one of these. And here's TRAPPIST-1C, which we have a program on. My PhD student, Alexander Radke, is leading. And then what you notice, though, is that when you go to the sort of the temperate small planets, they're completely dominated by this wonderful TRAPPIST-1 system down here. All of these points say TRAPPIST-1, and that's because really TRAPPIST, as you've probably heard many times, is really a unique system in terms of transmission spectroscopy metrics that we can expect if the planets, of course, have atmospheres. But just from a detection perspective, TRAPPIST is really a unique system with these 7 transiting planets, and a number of them, depending on how you define the habitable zone, are in the habitable zone. And we're as I said, looking at TRAPPIST-1C, which has an very short orbital period of 2.4 days, and it's quite warm. It's not in the habitable zone. And the TRAPPIST planets have sort of densities that are compatible with Earth-like composition. And this is from Eric Egel's paper from 2021, and the masses here are from transit timing variations. And if you look at those uncertainties, they're compatible with rocky planets with secondary atmospheres, but they also seem to be slightly, more puffy than the Earth-sized planets. Of course, there's large uncertainties here still, but that could either be because of some volatiles in an atmosphere, or it could be because of the composition of the interior of the planets, or it could be because of the measurement, of course, and the uncertainties in deriving masses. This is not radio velocities. The system is far too faint to do RV follow-up and get masses of this type of precision for this type of star. I think the V is like 18th magnitude in V, and it's very, very difficult to get precise velocities. So the question then is, do any of these planets have atmospheres? And if they do, what is their composition? So we put in a proposal led by, as I said, my PhD student, Alexander, who's now at the CFA for a year, and he's returning to our group in the fall as a postdoc, where he got his own funding, which is great. So we put in this program, and this is from our proposal, to try to observe the atmosphere of TRAPPIST-1c. And these are three different atmosphere compositions that we looked at, and then we simulated whether we could detect the atmospheres of these planets. So the first on the top here is a 10-bar Venus-like atmosphere, a clear Venus-like atmosphere. And Alexander ran simulations on a cluster computer, simulating this hundreds of thousands of times. And this is the resulting sort of transmission spectrum simulated from JWST, assuming 4 transits. And we can with high statistical significance, we simulate the CO2 features in this type of atmosphere. And below, there's 2 different oxygen-dominated atmospheres. So this is a desiccated atmosphere, assuming that water has been photodissociated, the hydrogen has escaped. And we now have an oxygen-rich atmosphere, and we can detect CO2 trace gases in the atmosphere. And here's a similar one, where outgassing has been included to give you more CO2. So this is our simulations, and then the program was scheduled sometime last year, and we were basically set at the very, very end of cycle 1 to both our despair and relief. Despair because it was very late, but a relief that meant we had a number of months or time to build a pipeline. So we were scheduled basically in October and November in 2023. But last summer, my Alexander called me on a Saturday, and I was like, oh, there's something up. And it turns out that one of our transits was scheduled very, very early. In fact, this turns out to be, I believe, the first time JWST looked at an Earth-sized planet in an attempt to detect the atmosphere. And so, as you say, this is in July, and this was basically just before summer holidays. And in fact, I was downloading the data on a Friday before going on vacation. So this was a bit, and we hadn't really prepared any pipeline work, because we were expecting this to come in late October and November 2023. But fortunately, in our collaboration, people had already written some pipelines, so we had actually the opportunity to reduce the data with 3 different pipelines, and we now have another 4th pipeline that Alexander and I are working on. And so here's the transit of TRAPPIST-1c, and it's a beautiful light curve. I think if you have been in the game for some time, this almost looks like a hot Jupiter back in the day, what we would expect. But this is actually a terrestrial planet, of course, transiting a very small star. But the data quality is just amazing. There's some slope that we're not quite sure what the origin of that is, and there's still some work here in the reduction. You can maybe, if you squint, see some correlated noise in the residuals here. But this is a work in progress. This is unpublished data. We hope to publish this transit before this data before the remaining 3 transits. And of course, with this one single transit, we don't expect to be able to see any atmospheric features with the signal to noise that we had simulated. We really need the full 4 transits. And lo and behold, we see a very flat transmission spectrum of TRAPPIST-1c. And we're not able to discern any atmospheric features, of course, and we didn't expect to. The signal to noise we simulated was way below 3 sigma that we expected here. But the upside is that the signal to noise and the quality of the data that we're achieving is actually better than the exposure time calculator predicted. So in other words, if the planet has an atmosphere like we've simulated, and we're able to deal with stellar activity and systematics, and the planet actually has an atmosphere, then we should be able to detect it with these 4 transits. Of course, there's many caveats and ifs there, but at least JWST and the data that we're getting is really performing very well. Now there's this slope going on. You may be able to see here in the blue that I'll come back to in a minute, which we're kind of uncertain on the origin of that. But to compare with already existing data, we looked at data from HST, from Zhang et al. From 2018, and that's the red data points, I believe, as far from memory, I think this is about 2 transits. Comparing that to the blue data points, which is our data of 1 single transit of TRAPPIST-1C, and you can see the uncertainty in the error bars on the blue data points from James Webb are highly much better than what came out from HST from these 2 transits. So the data quality is amazing, and I hope that some of these planets have atmospheres so we can actually characterize them in the coming years. I think we're in for some excitement there. And just to sort of give you a sense of the features that we're looking for, this is the CO2 dominated 10-bar Venus atmosphere that I just overplotted on the data, and you can see that we are not able at this stage to be able to detect any of these quite small features with the precision that we're achieving with the single transit. Now this slope in the blue, we were a bit, well, that could indicate, of course, stellar activity. So we tried to model this with basically a very, very simple spot model. And you can sort of get this slope in the blue. And then, of course, there's some very large uncertainties in the very, very blue part of the spectrum. Actually, it may seem like it's turning up again, like it has a peak. And then you would have to make some sort of more complicated model with cold and hot spots, but we are able to simulate this with stellar activity, if that is what we're seeing, because then we kind of looked at the data in a little more detail, and this is a plot of our subarray. It's the sub 512S, so it's the smallest subarray you can get with near spec prism. So it's only 16 pixels in the cross dispersion direction. So this is the spectrum of the star TRAPPIST-1, and you can see that it peaks very strongly here in the beginning of blue. And if you actually look at the resulting median spectrum of all the integrations, this is what it looks like. And what we're a bit suspicious about is that if I draw a line here, I try to line these two up, the peak of the spectrum basically corresponds to this slope that dips, and sort of the bottom of the slope is where the peak of the spectrum is, and then that slope kind of corresponds to the flux of the star. And we at least discovered in one of the pipelines some issues because we were trying to remove the 1/f noise by subtracting the pixels that were on the edges of these orders. But this is a zoom in of this 3D representation of the host star, and I made some very strong cuts here in order to show you that actually we're cutting off, because of the small size of the pixel of the subarray, we're actually cutting off the flux, and it's bleeding out into the pixels that we're not actually recovering. And the reason we chose this was, of course, because of duty cycle to make a very fast readout on this small subarray. And we didn't want to saturate the instrument as well, so we wanted fast readout in order to get a high duty cycle. But perhaps this subarray is actually a bit too narrow. There's another one called 512 without the S, which is in fact 32 pixels. So we may want to change mode for the remaining 3 transits that we have, and we're kind of a little bit suspicious again of whether we're seeing instrumental systematics or we're actually seeing stellar activity. So that's still something we're investigating. Okay, so for the last 10 minutes of my talk, I want to talk about another project we're involved with, which is what we call the Second Earth Initiative Spectrograph, or 2ES. So the idea here is that we want to build a next generation extreme precision radio velocity spectrograph and put it on a modest sized telescope, but a telescope that's really dedicated to this project, basically trying to detect small planets orbiting solar type stars. So we're building this next generation extreme precision RV spectrograph, building on the sort of knowledge that has developed in the field. There's these new fantastic instruments like Espresso and Newit and Express that are these next generation instrument, Maroon X, as well. But are on telescopes where it's more difficult to make this high cadence observations of the same targets. And the idea is that we secured 2/3 of the time on this Max Planck ISO 2.2 meter telescope at LaCilla in the Southern Hemisphere. And the program we want to try to carry out is observe a couple of dozen, say 30 of the brightest solar type stars in the sky, and keep pounding away on these targets over a 5-year period, and observe them basically every single night, weather and visibility permitting, of course. And so the ambitious goal is to try to discover temperate terrestrial Earth mass planets in the habitable zone of the brightest solar type stars in the sky. And of course, that's a very, very ambitious and difficult project and goal. And two of the main issues, of course, is maintaining an instrument stability of say 10 centimeter per second over years, not over weeks. And that has been, I mean, the field is really pushing towards this direction. Sometimes some people are maybe a bit overly optimistic, and some are very pessimistic, and some are, so there's various, but I think we've seen data where we're looking at sort of 20, 30, 40 centimeter per second precision over timescales that are slightly longer. So the idea is to sort of combine 4 things: high resolution, high signals noise spectra, extreme precision radio velocities, high cadence of observations, so we can really detail the activity of these stars, and a long baseline, because one is the instrument stability, of course, and the other major issue here will be the stellar activity, which is going to be a massive issue trying to mitigate that, because we know these stars will be active even though we want to choose the brightest and most quiet solar type stars. Stellar activity is going to interfere, and we do have to figure out how to mitigate stellar activity down to that level, which is not solved and hasn't been done yet. But we believe that building a data set like this may allow us, at least that's the best, in our view, the best option to be able to really try to mitigate stellar activity. There's of course the sun, but the sun is not a very quiet star. In fact, it's kind of somewhat quiet, but there are other there are stars that are better suited for this than the sun. And that's of course all the solar telescopes. The data is wonderful, but we don't have that kind of data for bright solar type stars. So those are the types of stars we want to observe with the secondary spectrograph. And the hardware of the spectrograph is now funded. We have the majority of the funding for the hardware and laser frequency comb calibration that we envision for the spectrograph. And here's sort of the consortium. I'm the PI of the project. We have Thomas Henning and Laura Kreitberg from the Max Planck Institute, Andres Jordan, Andreas Kjörnbach, and Ansgar Reiners from Chile and Heidelberg, and then Andreas Seifert and Julian Sturmer, who were instrumental in building the Maroon X spectrograph, which Jacob Bean was PI on. So it's basically building on the knowledge from what went wrong, so to speak, with Maroon X or the other instrument. That's not the way I meant it, but building on the knowledge that we have from those instruments, because we can always try to do it as the precision as well as we can, but there's always issues that we haven't thought of that will be the obstacle for this long-term stability. So the spectrograph is about a resolution of 120,000, like many of the other spectrograph, and it's in the optical, going into slight into the infrared at 900 nanometers. And I won't go into all the gory details on this slide of the details of the spectrograph, but I do want to talk about target selection, because the question is, is there actually enough targets for a modest-sized telescope like a 2.2 meter? And if you want to look at bright photon-limited precision that's necessary to detect Earth-sized planets, defined as between 1 and 1.5 Earth radii, that gives us Earth masses in a Rocky composition between 1 and 4.5 Earth masses. Then we used Ansgar Reiners and Matthias Seckmeister's 2020 paper to do a target selection, and we come to about 1,000 solar-like stars, FDK stars, that we can observe, and we set sort of a maximum observation integration of 30 minutes, and that will lead to a single measurement photon limited precision at the level that will be able to detect the semi-amplitude of an Earth-like planet in the habitable zone. So there's a bunch of targets, in fact, that are bright enough, and we have worked on selecting an initial target list of 30 very bright, very quiet, and slowly rotating solar-type stars. In fact, we have a special proposal to go after 4 of these and try to make sort of a data set that is reminiscent of what we could imagine we're getting from the secondary spectrograph. And already we're running into problems. We want to use espresso every single night to observe these 4 targets that we got time on espresso, but that's really difficult to schedule. And that's kind of the point of the spectrograph that we're trying to build, is to really get a very high cadence, detailed data set. And of course, there's also another project that you probably have heard of, which is ARPS-3, or the terror hunting experiment, which will be is a very similar type of spectrograph, or at least the goals of the spectrograph are the same, which will also be on a 2-meter class telescope, but in the Northern Hemisphere, so it's very complementary to our project. And so the idea is, of course, if radial velocities is able to do this, I believe this is the way forward, and we would discover planets that would really leave a legacy, a lasting legacy, because those will be the targets that are the best for next generation upcoming space-based telescopes that can observe, or will try to observe, the atmospheres of these planets. And we can sort of see when we're I'm in the Andes working group on that spectrograph for the ELT, and it's really, one thing is knowing the occurrence rates of planets, but actually having targets to specify to help specify these next generation instruments. It's incredibly valuable when you're trying to figure out what signals noise you can achieve, and so on and so forth. So having these planets would be tremendously exciting for the next generation telescopes. Also, that would also alleviate the need for a direct imaging survey with a very large telescope like one of these. This is from the Duvar pre-decadal survey, that video. But as you may know, or many of you probably know, the decadal survey recommended a very large class infrared optical ultraviolet space telescope with the goal of observing the atmospheres of terrestrial planets, and it's now, I believe, been called the Habitable Worlds Observatory, and is starting to go into the planning phase. So the idea would be to try to find targets rather than to do sort of a direct imaging search with such a large telescope, which would be very costly and difficult, if it's at all possible. Of course, I reserve the option that we cannot alleviate stellar activity down to the 10 centimeter per second level, but that would also be a result, although it would be slightly disappointing. It would be important to know if RVs are simply not the way to go to detect Earth analogs around solar type stars. So with that, I want to stop my talk, and I'm happy to discuss and have questions. I do want to just say that we recently got a rather large grant, and we're going to be hiring a number of PhD students and postdocs over the next 5-year period. So if people that are listening are interested in this, please don't hesitate to contact me, or keep an eye out for calls for applications in our group. So thank you so much, and I'm happy to discuss.
Thank you very much, Lars. That was great. We clearly have a lot to look forward to over the next few years, and I also appreciated the dive into pipeline systematics. It's not, you don't always hear that in talks, and it's great from a theory perspective to see some of the inner workings that goes into these things. So yes. The floor is now open for questions. Either raise your hand or just put your question in the chat. Completely up to you. So we have a question from Nick Cohen. Go ahead, Nick.
Yeah, so I don't know if it's a comment or a question, but have you put some thought into, with this kind of search for Earth-like planets around Sun-like stars, even if you can't actually detect true Earth twins, just the upper limits you would get would still be super useful for a direct imaging mission, because when we start seeing a dot in direct imaging in reflected light, we will have no idea what mass that dot is. And if we could at least rule out any like Neptune or sub-Neptune scenario, then we would at least know that we're looking at a terrestrial planet, even if it had not been detected previously with RV. Yeah,
true. I mean, we know this from all the transiting follow-up, RV follow-up that's been going on, right? It's much easier when you know there's a planet and you know where to look than the blind RV, the rocky planet searches that also goes on. So I think if you, as you say, detect like say a dot and you think there may be a planet there, having that constraint and then having the RVs would actually be very, very useful. We haven't looked into that number and we haven't estimated what that could sort of mean in terms of upper limits, but it's certainly true that if there's a detection from some other type of observations like direct imaging or transits, then it's actually much easier to look at the radial velocities afterwards. So that's certainly something that can be done if those targets that we're looking at, that data set will be there once these direct imaging missions might fly later in a couple of decades, I guess.
Yeah, and I mean, just to follow up on that point, I mean, for good reason, Earth-like planets around Sun-like stars are kind of the most exciting, but there's a huge science case for other types of rockies or even up to sub-Neptunes in habitable zones around Sun-like stars as well. So I'm wondering, for the 2ES science case, is that part of what you're proposing?
Well, I mean, yeah. So there's no, I mean, these terrestrial planets in the habitable zone are not going to be alone, right? So sort of the auxiliary payoff would be hopefully that we discover a number of planets in what I expect would be multi-planet systems, and also tease out the masses of larger planets in these systems as sort of a side goal. But the main thrust of the project is really to make this giant leap towards trying to detect terrestrial planets in the habitable zone of solar type stars, which is incredibly hard. And as I say, I know people are skeptical, and it may be that this is simply just not possible to overcome the stellar activity at this level that's there. But I think this is the best way of trying to do so, in my view.
Yeah, centimeter per second stability over years. It's not easy.
That is not easy, no.
So I have a question from Frederic Schmidt.
Hi, very nice talk, thank you. Maybe a naive question. Is that possible to make the difference or detect a moon that could be around those planets, and especially on the JWST data? Because if I understand well, you have to combine different observation to have something for the atmosphere.
I think, well, I'm not an expert on moons, but I know David Kipping very well. I was sitting next to him for some years in the office next to him at the CFA. And I mean, I think my understanding is that large exomoons have sort of been ruled out, that like the size of the Earth or something like that. So you really have to, exomoons are extremely difficult. And so I think, I don't know if you're talking about detecting or just detecting an exomoon or characterizing it, but I'm not an expert, but I think it will be very difficult. They're very small. If you look at the moons in our solar system, they're just so much smaller and more difficult. So it may be very difficult.
Okay, so the Earth's moon size, for instance, would be completely out of the signal to noise to detect.
Yeah. I think so. I mean, what David did, I remember, was take, for example, many of the Kepler planets systems and sort of stretch the transits to allow them to stack multiple systems on top of each other. And then if there were moons, you might see sort of a little dip before the ingress and egress. And he has some upper limits there. And it's, it rules out very large moons, at least, sort of the same size of binary planets or something like that. And so it's really, really difficult to detect moons. But
okay, thank you.
Additional questions for Lars? So I guess I have one about the TRAPPIST-1c observations that you're doing. You're obviously initially just looking for any kind of detection or non-detection of an atmosphere, but I saw you were simulating 10-bar O2 atmospheres and also CO2 atmospheres. Am I right in understanding that you're not going to be able to detect O2 directly? It's just going to be the background gas in this sense. So you're looking for signals of CO2 or possibly H2O.
Yeah, O2 is out of the question. It's just as a background gas. So it's a CO2 trace gas in an oxygen-dominated atmosphere is what we were. I think it's from is it Minkowski? I think that did these simulations, I believe.
O2 collision-induced absorption doesn't help you at all in the James Webb spectral range.
I don't. It's very difficult to detect O2. The main features is just in the very, very blue part of where you see the uncertainties explode in the PRISM data. So that's going to be extremely difficult, I think. I would be happy if we see any species at all.
Right. Yeah, that's obviously the primary objective. Tim.
Yeah, I have a follow-up question on that. So with the data you got already, can you sort of better understand with the following transits that are already scheduled, how that the data acquisition actually will differ from your predictions before the first measurements were taken? Can you refine, or can you already see how the follow-up measurements, how they will get you?
Yeah, are you talking about signals noise, or are you talking about, so I mean, barring stellar activity and no atmosphere and things like that, and also systematics that we're unaware of, just the pure signals to noise is actually better than the simulations predicted. And so that's really encouraging. I think most of the instruments are actually performing better than expected on James Webb. And so with that in mind, I think we're actually going to get better signals to noise than we simulated. Of course, then there's all of the things that you're not aware of, like systematics or stellar activity and unocculted spots, or all these things that can make it much more difficult. And TRAPPIST is probably a somewhat active star. The initial observations indicate we see slopes in some of the other transits that have been observed, not of our data, but in other. And some of the other transits are completely flat and with no stellar activity. So I think that's probably going to be the main issue. And of course, then the next question is whether these planets even have atmospheres at all. I know Lord Kreitberg has a data set on trying to also look at TRAPPIST-1c that has been observed by doing secondary eclipse measurements and looking at whether there's a heat distribution of the atmosphere, and thus trying to look at the binary question: is there an atmosphere or not? And those data have also been taken. So the word is still out, but we'll see whether these planets have atmosphere. But I think the data looks very encouraging in terms of signals to noise. It really looks encouraging.
Yeah, and to follow up on that a little bit, this is kind of a question about unknown unknowns. But if you were for a general audience to say how you think the systematics evaluation is going to develop for James Webb and what we should expect going forward, do you feel optimistic generally that the kind of initial problems we're seeing now are going to lessen as understandings of the instruments improves?
Yeah, I think the general community feeling is that it's actually very well behaved, and there's compared to maybe Hubble, there's much fewer systematics, and the community has also really come together to put together a number of different pipelines to look at this. The trouble with our observations in particular is that we have this extremely small subarray, which we chose due to cadence and signals to noise. We basically just try to optimize as much as possible and get as many photons as possible. But then now being wiser and looking back, we may not want to use this very narrow subarray, because there's a number of data reduction issues and systematics that are difficult to deal with when we have this very narrow. As you saw in one of my plots, the flux actually spills out over the edge of the detector, and that's, so we're kind of, it's very little, but we're still not capturing all the photons that we're getting. And so when we're trying to, for example, remove systematics like this 1/f noise, which is basically a detector noise that changes from column to column, that makes it very difficult. So I think general consensus is that we will have the systematics under control, but we need to understand which instruments and what modes are the best for these observations. If we go to different subarrays, for a planet like TRAPPIST, or a star like TRAPPIST-1, there are data points that will completely saturate in the spectrum. And so, for example, I know that there's observations of TRAPPIST-1G with the near-spec PRISM instrument, and they chose a different observation strategy where we're doing a ramp of 3 reads outs and then a new integration. They have 6. And so in the peak of the flux, they will saturate many of those ramps. Also, they have a slower readout because they have a larger detector. But I think perhaps that is a better way to do it, actually. That wasn't our initial assessment, but now that we're looking back, there's so many unknowns when we're writing proposals and trying to, configure them without knowing all the details. Of course, I hadn't even heard of 1/f noise at that time, so I wasn't even aware of the issues we had to do. But I think the general consensus is, that was a very long-winded answer, sorry, but is that the systematics we'll be able to get this under control, and I think we'll then optimize what kind of modes we'll be observing, and that will give us the best data.
Yeah, thanks for the response. It's interesting to hear how things are evolving so quickly. We got a comment from Nick in the chat as well. I think a comment rather than a question. He says, repeat observations are definitely key. James Webb is operating beautifully, but TRAPPIST-1 is constantly messing with us. No 2 observations are exactly the same. So yeah. Stellar activity, obviously, always.
Yeah, I know there's community efforts to try to really, there's a proposal, I believe, that's trying to stay on JWST. Maybe Nick, you're a part of that, to really stay on stay on TRAPPIST-1 and try to really understand the stellar activity with James Webb. So that's definitely going to be important.
And dwarfs both opportunities and challenges. Do we have further questions for Lars? So I guess one more thing I could ask on the sort of observation versus theory side. It kind of, as observers, of course, you have the luxury of just looking at something and seeing what you find, and that drives the theoretical development. But I'm curious, nonetheless, for the TRAPPIST system, if there are sort of specific atmospheric loss theories you're thinking about comparing with, or processes that you think may be most important in that system for determining the line between airless bodies and those that retain some atmospheres.
Yeah, that's a good question, but it's really, I think that's a tough question, because I think we know so little at this point that detecting the first atmospheres will be really important to figure out which directions to go. So another thing we haven't discussed is clouds in the atmospheres of these planets. And that's of course a major problem if all these small planets exhibit like high clouds or hazes in their atmospheres. And so that our program was tailored to detect an atmosphere if it's rather a clear atmosphere. Now, if it's a cloudy atmosphere, it would be excruciatingly hard to do and require many, many more transits than the 4 that we've asked for TRAPPIST-1c. And so our philosophy was, let's try to see if we can detect clear atmospheres around these planets. If not, then either there is no atmosphere or it's a very cloudy atmosphere. In either case, there will probably be more interesting targets to spend the time of the precious JWST time on, because if they're very cloudy, it will just require so many more transits to even, begin to detect any atmospheric features. So I think to me that the hunt now is to find clear atmospheres on terrestrial planets if they exist, and try to characterize those with the precious time we have of JWST, and sort of find those fantastic planets that we can actually do some characterization of. I don't know, that's not a very good answer to your question, but right now I would ask you the question, Robin. Actually, that question you posed me, really.
I was just in fact, I was just about to respond by saying it'd be wonderful if theory could give some guidance about where we expect clouds to appear or not. And there's certainly work being done to try to accomplish that, but clouds are, as everybody knows, an extreme challenge. And I think even in some cases for ruling out H2, HE atmospheres, if the clouds are high enough, you're still going to have problems even then. So I suppose the solution is continued intercomparison of theory and laboratory experiments. I think laboratory experiments in particular are really important because we just don't have some of the data in the range that we need, particularly for haze formation right now. But yeah, ongoing challenge for sure. If anyone has anything to add to that. Okay, well, if there are no more questions or discussion points, I suggest we wrap up there, and those of us on the East Coast can go and get some breakfast. I want everyone to thank Lars again one more time for an excellent presentation. And Tim, I don't know, do we have any Rocky Worlds discussion related announcements before we close?
Yeah, I mean, the next seminar is on 6th of April, Thursday, but the speaker is currently still in discussion, so we will announce this just using the website and mailing list.
Excellent. All right, thanks for joining everyone, and thanks again, Lars.